Okay, we are recording now. So it is 26 August 12:30. So we are doing linear algebra tutorial 1. So this is right. Lost my screen. Okay, I'm going to share my screen first. Now, are you seeing my screen, guys? Yes? Now, if you have any problems, if you cannot hear me, see me, or whatever, because yeah, I'm not so familiar with this, please let me know. So I hope you are seeing the slide that I have put up in Adventure. And in this slide, you should be able to see the second slide, which is the important slide for you. The first link is the YouTube link, in which we basically put all the answers in the YouTube. It is basically a recording of me going through all the answers. So maybe I would go to this link now, and you will see this link here. So it is named plainly as tutorial 1 linear algebra. And in here, you see tutorial 1, question 1 to question 11, all the questions. So you can go through it by yourself. And if you do that, then in this lesson, in our online discussion, I can then answer other questions that you may have. Now, if you have no other questions, then I can just go through some of these questions in slightly more detail, and then we can have a slightly more interactive session. That's the whole point. Okay, so I hope that you have gone through some of the questions. And then if my handwriting is not very good, or you cannot watch the video very clearly, you can pick up the PDF from here. There are 2 Dropbox links. Please pick up them up soon, and then I can remove them after this. So basically, the PDF links are exactly what I have used on the videos. And then there's one additional link which I have wrote. So basically, maybe I'll use today's online lesson to go through them if it is useful. All right. Now, what about the rest of the slides? It is basically things that I have found to be useful, and then you can also go through them as well. For example, like the MIT gone through geometry and going from equations to a line, and then what is the unique solution, which is the intersection of points. So we also go through that, but she did it very well. So there are many others that you can use as well. So basically, I highlighted what I found to be interesting, and then yeah, you can just check out the videos at your own time. Now with that, right, yes, okay, chat. Will the slides be uploaded? Yes, the slides is here. Here, these are the slides. Okay. All right. So you are still seeing my screen, right? I hope. Yes. Okay. Great. Now, so I'm going to switch screen. Where's my reflector? Close this one now. And I'll bring this here. Okay, so we can go through the tutorial proper now. Maybe I'll just try this question again. And then if you all have any questions, I will stop. Okay, so please feel free to interrupt me anytime. Now, the question is basically given a matrix A, we are asked to check whether can B be found through AX. Chat. As in, will we have access to the PowerPoint file to access all the link? Yes, the PowerPoint file is in Adventure. Okay, let me go through that. Can you go through Adventure and go into part 1? Under the announcement, I said the PowerPoint file is released. So that was the PowerPoint file I've shared. Okay, Hong, can you check? Okay. Now, may I ask you all to turn off your mics if yeah, so that you'll be a bit quiet for everybody. Okay. All right. So the question basically says that let us find let's check whether we can solve AX equals to B. But he didn't word it that way. His exact wordings are, let's see. His exact wording are given the columns denoted by A1, A2, A3. So he basically make the columns and then call them A1, A2, A3. And then he created a variable called W, which we call it a space. And then he said that this space is spanned by these 3 columns, A1, A2, A3. So what he means is that basically he says that W is a space spanned by these 3 columns of A. And what it really means when we say W is spanned by columns of A, we are saying that W is any linear combinations of A1, A2, A3, which basically also means that we are allowed to multiply A1 by any scalar x1, A2 by any scalar x2, and A3 by any scalar x3, and we are adding them together. So the word linear combination has 2 implications. Linear here means that when we multiply by something, that something is only a scalar, and then combination here means addition. So immediately we are given this equation, and then we have y. Y belongs to W, the set of all vector. All right. So once we have that, so basically he's telling you that I'm creating a space with 3 vectors, hopefully pointing at different direction, and then any this space belongs to W. And now this question is, does B belong or is one of the element of W? So the first question, of course, is how many elements are there in W? Guys, any idea? How many elements are there? So the answer is actually infinite number, because I mean you are doing any linear combinations, so you can basically multiply A by anything, and therefore you have infinite. Now if you have only one A1, then basically you can only travel along this A1 direction, whether it is blowing it up or making it smaller, or multiplying by minus means going against A1's direction, going the opposite direction. So if this is A1, my pen, then you can go higher along this way, or in fact opposite way. So that's the idea of multiplying by positive value, making A1 bigger, multiplying by negative value, turning the vector around and pointing it in its opposite direction. By adding, it means that now I can add A1 and A2 scaled by different values, and by this nature I create a plane. So in the class, I always drop my pen on the floor, one of them pointing in the X direction, one of them pointing in the Y direction, and therefore now any combinations of these 2 pen scaled by different values give you the whole floor. Okay. Now, so how do we solve for B in W? The answer is that in our particular case, it's easiest to solve by Gaussian elimination, because we are in Gaussian elimination, you are basically solving AX equals to B, find the X. What you then do is that you put A and you put B together in the augmented matrix, and then you're basically doing a lot of row reduction, and then you're hoping to find a matrix that looks like this. Some new B's, not X, not 0, some new B's, some values, but zeros here. If you can solve it this way through Gaussian elimination, the squares are called the pivots. And then remember that we, in this particular example, our A is a 3 by 3 matrix, and we should find, or not, we must find 3 pivots. If we find 3 pivots, then we have a solution. Okay, so what did we just do in our problem? Well, we start with A. We put the augmented matrix. We start to perform Gaussian elimination. So here, the word R3 equals to R3 plus 2 times R1 simply means take the third row. This is R3. Take R1, multiply by 2 times R1, which is 2, 0, minus 8. And we add to R3. So all these are mechanical, and you can do it quickly. Just don't make a mistake. And then we finally reduce to, in the first step, this form. The second row, we didn't do anything because the second row already have a 0. So in the mechanics of things, what are you trying to do? You are trying to basically reduce the second row with a 0 here, the third row with a 0 here, and the next process a 0 here, so that you would have an upper triangle matrix. Values only fill on the top right hand corner. And once you have filled up in this way, then you can solve the equation by something called back substitution. All right. So let's assume that we can do all the Gaussian elimination and we reach this point. 1, 0, minus 4 for the first row equals to 4. 0, 3 minus 2 equals to 1. 0, 0 minus 1 equals to 2. Why are we interested in this form, you may ask? I mean, why did we go through all the trouble? Well, first is that in this Gaussian elimination, it identifies the pivot. So the red boxes are the pivots, and we can count them. We can count only non-zero pivots. If the pivots are 0, it's useless. There's no pivot there. So here we say number of pivots equals to 3. All right, so what does the pivot do? I mean, why would the pivot be interesting? Let's look at the last row. In this last row, the equation is actually, remember the first column is with respect to x1. The second column is with respect to x2. The third column is with respect to x3. If we write the equation like this, 1, 0, minus 4, 0, 3, minus 2, minus 2, 6, 3, x1, the first variable, x2, and x3 equals to 4, 1, minus 4. We are asked to solve for this. So when we put in the augmented matrix, the first column corresponds to the scalar multiplied by x1. x1 will multiply the first column. Right. What is interesting is the last row. The last row's equation looks like 0 times x1 plus 0 times x2 minus 1 times x3 equals to 2. Now, I'm going to draw the pivot for you. Now, here is useless, all the 0 multiplied by x1 and x2. The only thing useful was minus 1 times x3, implying x3 is equals to minus 2. So it is immediately obvious to you now that with pivots, we can find the variable associated with the column. We have 3 pivots, we can find 3 variables solution. What about the second one? So once we can find the last one, what about the second one? Let's try. Oh, there's some chat. Let me find out what you want to ask. W is a plane in 3D space geometrically. Okay, wait. So let me finish this first. Right, the second row is telling us this equation. 0, x1 plus 3x2 minus 2x3 equals to 1. Since we have already solved for x3, which was minus 2, we basically can reduce the equation to 3x2 plus 4 equals to 1, implying x2 equals to 1 minus 4 is minus 3 divided by 3 is equals to minus 1. So the basic idea is that we can just do all these elementary row operations reducing to the number of pivots. And once it is in this form, which is a form suitable for the technical term is back substitution, meaning that we are substituting and finding the variables from the back, then we can solve the equation. All right. Now you can go through the mechanics and we found these 3 axes. So what does this mean? We have the A, we have the X, and then when we compute this, we get the B, exactly what we want. So therefore, we can say that B can be found in the column space of A. That's one way we can say. B can be reconstructed using columns of A, which is what this guy is asking for. Is B in W? Does B belong to W? What is W? W is the span of the columns of A. So they're all asking the same thing, just using slightly different lingo. All right. So Nico asks, is the ERO, elementary row operations, denoted by R3 equals to R3 minus 2R2 instead of R3 equals to R3 minus 2? Is there a preferred format? No, you can do whichever. It doesn't matter. What happens is that when you do elementary row operation, you might not get the same final form. Okay, you might not get. Only when you do reduced row echelon form, then you get a unique form. So let me pull out Wikipedia. This form that we have just shown on the left is called row echelon form. You can do one more step called reduce row echelon form. Okay, and then you still can solve. But it's up to you. I'm lazy, so I just stop at row echelon form. So I now pull out reduce row echelon form for you. Okay. So we go to wiki and where's my reduce? With reduced row echelon form, there are more zeros on the top as well. Okay, so you can take a look. So the take back message is that row echelon form is not unique because it depends on which row operations you have done. In reduced row echelon form, it is however unique. Okay, now let's continue. So is everybody convinced that this is the correct answer? Now, if you are sitting in front of a computer, my suggestion is always to do this. I'm going to move my screen. I'm going to move this a bit outside. Now you can see my MATLAB, right, guys? So what we normally do is that we just type A, the matrix A, which is what is given to us, and we type the solution we have found, which is B. 4, 1, 4. Did I make a mistake? 4, 1 minus 4. Oh, so I did a typo here, right? I guess. 4, 1 minus 2. Let's see. 1, 0 minus 4, 0, 3 minus 2, minus 2, 6, 3, times 4, 1. Ah, I see 1. What's the error now? So the answer is minus 4, minus 1, minus 2. So x is equals to inverse of A times B. A times x is equals to B. 4, 1 minus 4. Okay. In your later class, you'll learn something called the inverse of A. So we have given you A, and there's a matrix called inverse of A. Inverse of A can be thought of as like 1 over A, but of course you cannot do 1 over a matrix, but it behaves like 1 over A, 1 over something. So A times 1 over A equals to 1. So the identity. So I'm going to show you A times inverse of A is the identity matrix. So identity matrix is only 1 in the diagonal and 0 everywhere else. There's some funny numbers here, so it is because of numerical precision. All right. Now, so let's continue. Okay, we have chats. Some more. Hi, Prof. In the case for question 4, we can use 2 methods. Either get row echelon form and do back substitution, yes, or get reduced row echelon form and get the answer immediately. Yes, that is correct. Inverse and transpose of A is the same thing? No. A is this, can? Or in fact, inverse of A, that doesn't look anything like transpose, yeah? Only some very special matrix is transpose is the inverse. And this you'll learn in the second part of this course. These are called unitary matrix. Its inverse is the same as its transpose. All right. So are we happy with question 4? Okay, if we are, then let's proceed. Are the fonts too small, guys? Everybody? Is the font too small? Okay. You're looking at my screen still. Okay, I minimize this, make this bigger. And now let's see the question. Now the question 5 is this. We have 3 vectors, W1, W1, W2, W3, U and V vectors, Rn. Now what does Rn mean here? So let's introduce some notation. R is the real number. So when I use the notation X belong to R, means X, the variable X, is a real number. So here is belong to, okay? And R here is the set of real number. So I can say Y belongs to C. C is the complex number. What about Z belongs to R2. So here, the 2 here, basically you can think of it as R times R, the Cartesian product. And remember, when we have a Cartesian product, we draw. So here is 1 R, and here is 1 more R. Okay? So we now have a plane. And how do we represent R2? In the vector format, we just have element 1. Let's call this x1, x2. And here will be x1. And here is x2. And this point is this guy. Everybody clear? So the notation here basically mean, if you want to understand the geometry, means that V is a vector with x1, x2, xn. And this n, of course, is this n. So in our course, we play with n equals to 2, 3, 4, any integer numbers. Yeah, only integer numbers n. All right. So we are now asked, we are now told some conditions. We are saying that we have a span. So again, remember, span means that, let's call the span W. We use the big W to represent a set. And what is this set? A set of vectors that is some, for example, some x1 multiplied by w1 plus x2 multiplied by w2 plus x3 multiplied by w3. X again are real numbers. Okay, all these x are real. But these w's are not real. The w's are Rn. Okay. So basically, what we need you to think through this is, we are saying that we have a vector, 3 elements. Let's call this W1. And when we multiply x1 with it, let's have the element A, B, C just for fun. And then this notation, x1 multiplied by w1, is the asking you to do this x1 times A, x1 times B, x1 times C. Okay, so let's have a concrete example. If x1 is 2 and ABC is 3, 4, 5, then of course the answer is 6, 8, 10. So that's the idea. So now we realize that every time we multiply a scalar with a vector, all the elements are scaled. That's all. And we can add all these up. Okay, fine. So at the end, we are getting also a vector. Here, 3 elements. But how many different elements can I put in W? An infinite amount of them, spanned by this W1, W2, and W3. Some linear combinations of it. So the question now asks, if U and V are already belonging inside the W, the big W, then is the sum of U and V also in this W? And I mean, from a very logical perspective, we must hope, right? I mean, I think, you see, in the big idea of this is, I give you one vector, I give you another vector, and I want to add them up. And the question is the sum of these two vectors still in the space that I have asked you to work on, which is W? And we hope that it is in a space and the word is close. Is vector addition, so these are vectors, and we are adding. Is vector addition close under addition? So in English, it basically, or in layman's term, it basically means, after adding, do we still find the sum vector in the original space that we are working in? All right. So to answer the question, we have to understand something. We have to really understand what is span. Span is nothing but a linear combinations of these three vectors, okay? And how to produce a linear combinations? Let's take U1 first and says, let U1 be some constant 1 multiplied by W1, some constant 2 multiplied by W2, some constant 3 multiplied by W3, where the constant is a scalar. So that's the definition. And we are adding them up, which is the definition of combination. So we are adding linear combinations. So we're happy with the definition of U, and we don't care what C1, C2, C3 is. We are saying that U can be formed by any multiples of C's with the W's. Same with V. Now V, we choose a different variable. Now we choose D1, D2, D3, multiplying by W1. And now we say let's add them up. Now, then it's obvious that C1 W1 plus D1 W2 can be distributed like this. So you can convince yourself, for example, you say C1, let's say, for example, A, C1, B, C1, C. This is C1 representing W1 plus, for example, D1 let's call this X, Y, Z. This is D1 W2. So this is C1, this is C2. And then of course, when we see that the matrix in this form, by brute force, we know that we can perform this distribution. C1 times W1 plus D1 times W2 can be written in this shorthand. Now, once we have reached here, then again, we realize that C1 plus D1 is a scalar because C1 is a scalar, D1 is a scalar, C1 plus C1 is another scalar. Let's call this, F1. And then here's F2, and then F3. And then we're back to the same idea. It is some scalar multiplied by W1, some scalar multiplied by W2, W3, and we add them up. And isn't this the definition of the vector is in the span, or the vector is created by linear combination? And yes, it is. And therefore, we can conclude that the sum of U plus V is also in the span of this. So I mean, with that, I mean, you understand how to answer this question. Right. Anything? Okay. Question 6. Now, let's read the question first. Question 6 have two parts, A and B. I'm going to only do the first part. A is a 4x4 matrix. B is also a 4x4. In fact, A and B are the same questions. A is a 4x4, so he first asks you, how many pivots are there in A? Does the equation AX equals to B have a solution for each B in R4? Or basically he's saying that any B I choose, is there a solution? So let's try to understand this. Basically, I'm given A. The problem is, can I do this? This is a 4x4. The vector X must be a 4x1 column vector, and B will therefore be a 4x1 column vector. So in fact, we don't like to write 4x1. So what do is that we just simply write like this, and we say that X belongs to R4. We don't even write 4 by 1. Yeah, here we can write 4 by 4, but we are lazy. We'll never write 4 by 1 if it is by 1. All right. Now remember that for matrix multiplication, the size matters. So if our A is a 4 by 4 matrix, this guy must be a 4. If it's not a 4, we cannot do multiplication of matrices and vectors. Now the second value here can be anything. It can be 2, can be 3, can be 1. What happens is that if in this case it is 1, then basically the final size is, this guy must match, and the final size is 4 by 1. So B is 4 by 1. So if you remember your A levels, basically this is asking you to check whether the size of the matrix multiplication are they consistent or not. And if they're consistent, then we can do multiplication. Right. Now, let's interpret the question. He says, does it have a solution? So basically he's asking you, can I find a x given A and B? So given any B, given the A being fixed, any B, can I still find x? Now, how many B's can he give you? He can actually give you any numbers, any 4 numbers, right? So if you think, what are the possible B's that I can construct? What possible B I can construct? Then this question is exactly the same as, what is the span of column of A? So I take this guy, take this guy, take this guy, take this guy, and find the span of these 4 vectors. If I can find the span of these 4 vectors, then I know where all the B's can land. Okay, but that's how we want to understand the problem. But how to solve the problem is actually much easier, because he already give you the clue. If you can find the number of pivots, and I have 4 variables here, let's call this x1, x2, x3, and x4, because I'm going to do it this way. Why do I put the x1 on top of the first column? It's because you realize that matrix vector multiplication is doing nothing but x1 times the first column plus x2 times the second column plus x3 times the third column plus x4 times the fourth column. Now, prove it to yourself that this is true. Once you understand this, you understand that I'm putting the variables on top of each column because I want to identify who they are multiplying against the column. Now, if I have 4 variables because I have x1 to x4, to solve for them, I need 4 pivots. Remember, the pivots help us to solve the variables. If there are only 3 pivots, then something is going to give. Okay? So in this question, if you just want to do it mechanically, the answer is, for any B to be to have a solution, there must be 4 pivots. If there are no 4 pivots, we cannot solve 4 variables. Okay, let's try. So we have the A. We start to do elementary row operations. So this is the first elementary, second elementary, third elementary, and keep on doing it. And we are left with this guy. On the right hand side. Okay. So immediately it's obvious to us that there are only 3 pivots. So we have 3 pivots, 4 variables. So what happened? So not every row has a pivot. Therefore, there is 3 pivot and 1 free variable. So What it means is that well, if we don't understand, we'll just say that because there's no 4 pivots, therefore Ax equals to B does not have a solution for every B. Now, you might ask, then which B? Which B can be found? Okay, think hard. If not every B can be found, which B can be found? Okay, now the answer is, of course, x1, x2, x3, x4, x1 times the first column, x2 times plus. The B that can be found are linear combinations of the columns of A. Those B's that are found in the linear combinations of A can be found. Then you might be wondering, but I'm allowed to choose any X. Why would I not be able to find, what do you call that? A B that is found by these linear combinations. Okay, now to do that, I'm going to digress and go to this one. Okay. Now we have about 15 minutes left, so let's try. I'm going to go through the interpretation of one equation, two variables. Two equations, two variables, three equations, two variables, and we want to understand what it means. One equation, two variables. Typically, we give you y equals to some function of x, and here we do y equals to minus x plus 1. So let's graph this. How do we graph this? We know it's a line. So we say let x equals to 0, y is equals to 1. Let y equals to 0, x equals to 1 as well. So this point and this point, and then allowing me to draw the red line. Clear? So when I give you an equation, this kind of equation, linear equations, then I'm asking you to draw lines. Now there are two variables, x and y, and then it forms a line. Now, every time we ask you, find the solution, find the solution. So what is the solution? So and the solution is always found in the matrix form. Okay, fine. So now let's go from this equation to the matrix form. So y equals to minus x plus 1. So I want to do the variables on the left-hand side. So I do x plus y equals to 1. So everybody with me. We then want to write it in matrix form, matrix vector multiplication form. 1, 1 times xy equals to 1. Okay? Now, at this form is also very, very close to matrix vector because here, then you now realize every equation is a row in A. So this is A, the first row of A. So one equation is one row of A. What about this guy? So this is AX equals to B. Oh, B is actually the constant of the equations, the original constant of the equation. What about the X, the vector X? Oh, it is the what? It is the variables X and Y. Oh, okay. So now, please interpret going from one equation to the matrix vector representation. Okay, so once you have done that, then what else do you want to do? Now, if I've only given you one equation, you can also imagine that if I've given you another equation, they're all zeros. That's one interpretation. I've given you one equation, but if I've given you another equation that is totally dependent on the first equation, then basically this will happen. All right. Then when we do row reduction, there's nothing to do because it's already in reduced form. We can identify the pivot. There's only one pivot. And because there's two variables, x and y, therefore there's one free variable. Okay. So now let's find the free variable. So how are we going to find the solution? So every time when we talk about the solution, what are we talking about? We are asking you to find this guy. The values of x and y such that a multiplied by x and y will be equals to the right-hand side. So what are the values of x and y that satisfy this solution? Then and in this example, the whole red line, the whole of them, any values of x and y, you just read off. For example, if you read off this, x is equals to 1, y equals to 0. If you read off this, x equals to 0, y equals to 1. So if you read off this, so x equals to minus 1, y equals to how many, guys? Minus 2 or plus 2, right? And you know how to do that because, in fact, you know the equation. The equation says once you have given me x, I can find y because it's something minus x plus 1. So it might take you a little bit of thinking to go from what is the graph to what is the solution. And the solution is nothing but the graph, the line. The line that says this whole equation is true. That's the idea. Now, if you reach this point, then you'll be pondering, but in the whole other linear algebra, we are solving 3 by 3, 2 by 2, and our solution is unique. How can our solution now be infinite? Yeah. So remember, solutions to system of linear equations can be unique, means only one solution. Infinite means many solutions, or no solutions. So in this first example, I have just shown you that it is infinite. And the take-home message, why is it infinite? Is because there is one pivot and there's two variables. So implying there's one pivot and one free variable. All right, so let's go through how to find the solution. So we begin with this equation, allowing us to write. So we must perform row reduction, and then we'll get this form, and we are writing the equations as x plus y equals to 1. From this equation, okay, it must be from the row reduced form. Then we can say, let y equals to k. So therefore, x equals to 1 minus k, because y is k, and y is equals to k. So now we have the solution. X is 1 minus k. What is k? Any value. Yeah, any constant, because it's a free variable, because we know that y was free. Y is k. Okay, fine. We put it here. And then we don't like it in this form. We like it in parametric form, meaning that we want to put the multiplier in one side. So we take 1, 0 here, because this is actually 0 plus k. And we take the other guy out, which is k multiplied by minus 1 for x and 1. Now, when you reach this here, you realize that this form, describing this xy, is the parametric form of the same line that we have played with. And we are interpreting that this guy is called particular solution, drawn by here. And this guy allowing us to stretch up and down along this line. for different values of k. So that's the idea. Okay. Now, I have 5 minutes left. Maybe once you have understood one equation's two variable, we can now try two equations, two variables. The first case is I give you the second equation, but I give you a scaled version of the first equation. Just now was x plus y equals to 1. Now if I multiply everyone by 2, is 2x plus 2y equals to 2. So I've given you no new information whatsoever. I've given you a multiple of the first equations. Therefore, when I put in augmented matrix, the first equation and the second equation, then what happened is that when we perform row reduction, we get that problem which we have just said in the first example. Okay, so now we realize that, okay, I'm not cheating. It is true that we can have such an idea from one equation, from two equations. In fact, if I giving you the third equation like this, then it's the same. You have lots of zeros after row reduction. All right. Now, so we have case 1. Let's see the case 2, guys. Oh, let's end with case 1 first. Case 1 says, I have one pivot, one free variable, which is the same as the first example. Therefore, the number of solution is infinite. Okay, or no solution. No, number of solution is infinite or no solution. Yes, correct. Now, case 2, I've given you another equation, 2x plus 2y equals to 3. So this equation is not like the first equation, which was 2x plus 2y equals to 2. Right, never mind. We form the augmented matrix. We row reduce, and we get 0, 0 equals to 1. Oh, this is a bad news. What does 0, 0 equals to 1 means? What? So, well, okay. Remember that whenever we row reduce and we get such an equation, then the answer is one of the equation is inconsistent with the other equation, because it means that the right hand side will not agree. So how does it look like? Let us draw this graph. The first graph was the red line. The second graph is the green line. I should use the green to draw for you. So this equation here that I've just drawn for you is the green dashed line. And the red line was the previous guy. And the two lines, when I've drawn them, doesn't meet. There is no common point between the two lines that will solve the two equations. That is why the solution is, there is no solution. There is no meeting point. So that's the take-home message. Finally, of course, the last one is trivial. And then we can close this tutorial. Last one is I give you one equation that looks like y equals to x. And then I can plot y equals to x here. So the red line was previously, and the green line is new, and they meet only at one point. So the answer is there is one unique solution. There is only one solution. It's unique. How do I also solve this? I can put my augmented matrix. I can row reduce. I identify there's two pivots, there's two variables. Therefore, there is one unique solution. That's another interpretation. How do I solve for x and y? By back substitution, because this is very easy. Because at the pivot position, I can just substitute and solve for the variable. Back substitution means I take whatever I've solved and give it backwards and keep on solving. That's the general idea. So with that, I think maybe you can go through the third one by yourself. The third one is, I've given you three equations. They're consistent. So all the equations will meet at the same point. So the solution is still correct. I've given you three equations, but they are inconsistent. One of the equation is inconsistent of the other. So they meet at two places. So there is no one unique solution. Then do you say, but each of these meeting point, is it a solution? Yes, but only for a pair. But I need the solution to be agreement for all of them. So since they are not in agreement for all three equations, there is no solution. So that's the idea. Okay, so I think with that, I'm going to stop now. I think we're just running out of time. Are there any questions? And could you tell me if can you share with me if this is effective, this kind of tutorial is effective, please? Someone just type. Right. If you can send me an email as well, and then what I need you to do is I'm going to try to find this recording, and if I can put it up, I'll put it up. And if you have any questions, please send me an email. Yes, it's quite all right. Okay, great. Okay, so if you have nothing else, then I guess you guys can leave. See you next week. Same in Zoom. Thank you.